Hey everybody, today we're going to be looking at this problem on a satellite going around the Earth. All right, now it's obviously not circular motion, so centripetal motion is going to be a little bit more difficult to deal with here. You could look at the forces and you could figure out what the centripetal force is at this point, and you could deal with some speeds and things like that. But I want to teach you another way to deal with this type of question, the way that perhaps AP would like for you to do it. All right, so in this example, we have an artificial satellite that's in an elliptical orbit, so not a circle. Its the point of closest approach is 8.37 times 10 to the 6th meters. So that's right here, the closest, and that is from the center. Okay, so 8.37 times 10 to the 6th meters. And then the point of greatest distance is 25.1. So that's this one, 25.1 times 10 to the 6th meters. And then the speed of the satellite at the perigee. Now the perigee is the closest point. So our speed there is 8,450 meters per second. And the question is to find the speed at the apogee. Okay, so what is the speed here? That's what we're looking for. So let me first show you a demo that we did in class and see if we can make some connections between these two. All right? So I did this demo in class, but I want to remind you of what's happening, how it works. So I have just a disc here on the ground that rotates. Okay, it's not frictionless, but we're going to pretend that it is for the time being. So pretty close to frictionless, the closest that I've got to frictionless here. I do have two masses here, all right, which I'm going to hold out. And so I'm going to go ahead and give myself a little bit of a spin. And you'll notice I'm not moving very fast, but as soon as I move in, I pull those in, I slow down, I go faster, right? So again, just recognize that we start with the masses out, so I have a large rotational energy here. We start to spin. And as I bring the masses in, I change my rotational inertia. As I change the rotational inertia, my speed changes. And what's the connection between inertia and speed, angular speed? Well, it's momentum. And so momentum in this principle is going to be really, really important. Now, I'm going to take you back to the problem with the Earth and the satellite, and I'd like for you to try to come up with and think about the connections between this situation with me holding the masses out and the situation of the Earth with the satellite. All right? Let's go. Now, in that example, in that demo, what we saw was that when there was an internal force that was pulling the masses in, that it changed the angular speed of our system. Okay, I want you to think about the Earth as being me. That's the object that's in the center. Then you have the satellite that's out at the edge. Okay, the satellite that's out at the edge is the masses. Those are the two masses. Now, the force in my demo was my arms pulling those masses in. The force here is the force of gravity that's pulling the satellite in. All right, so as gravity pulls the satellite in, it should gain some energy, right? There's some work being done there. It gains some energy, it goes faster. And then as it starts to go away, the force is often working against that motion, which means it's going to lose some energy and lose some kinetic energy, and it's going to go back to our gravitational potential. Now, just like, remember when we did that example with the pulling the masses in, we did a calculation before that showed that energy was not conserved, right? We can have internal interactions in our system that can cause mechanical energy to not be conserved. And so we can't use energy here, or we could, but it would be much more difficult because we'd have to figure out exactly how much work is being done. A much easier way of working with this problem is to deal with momentum, is to say that our initial momentum is equal to our final momentum. All right, so we're going to look at the satellite here. We're going to look at the satellite's momentum. Its momentum should more or less stay the same. we're going to consider that the momentum of the Earth is going to change very little, right? Its mass is so big that its speed, its rotational speed, is not going to change very much. So we're going to consider the Earth to have a relatively constant change in momentum, or relatively constant angular momentum here. It's only the satellite really that we need to worry about. So for the satellite, remember momentum is rotational inertia times the angular speed, and that would be initial because the rotational inertia here is changing. So when we have the rotational inertia that's changing, it is a good idea to kind of start thinking about angular momentum here. Rotational inertia is changing, therefore the speed is changing. That's usually a good way to go about approaching this type of question. So now how do we deal with that? Well, remember the satellite is really, really tiny compared to the Earth. So we can treat the satellite as essentially a point mass. And remember that rotational inertia for a point mass is just mr squared. So that's the mass and then the initial radius. And then we're going to multiply that by our initial angular speed. And then over on this side, we're going to have the rotational inertia final, which will be mr final squared times the angular speed. All right, so at this point, we're ready to start putting in some numbers. We recognize that the mass of the satellite is not changing, so it's going to cancel out. We've got the initial radius. You can use either one as initial or final. I'm going to go ahead and use this as initial, and then we'll use this as final since that's what we're solving for. So the initial radius will be that 8.37 times 10 to the 6th. So that radius will be squared. Now, I don't have the angular speed, all right? But you may remember that speed is equal to angular speed times r. So we're going to go ahead and substitute for the omega v over r. Okay, please make sure that you write this out each time. Otherwise, students tend to do v times r because they're used to seeing the multiplied by r. Take time to write it out. Make sure that you get the correct substitution there. So we got the initial speed, which is that 8.450, which will be divided by the radius again, which still is that 8.37 times 10 to the 6th meters. That will be equal to now the final radius, which is that 25.1 times 10 to the 6th squared, times the final velocity. Again, we don't want the angular speed. We don't want the angular velocity, so we're going to go v over r again, so that 25.1 times 10 to the 6th. Now, at this point, you can kind of make a decision. You can just punch it into your calculator just like that. Your calculator, if you have, one of the ones that's appropriate for an AP course, you should just be able to punch in that equation and it'll solve for v for you. Okay? I'm going to go ahead and show you how to do it algebraically just in case you don't have that. Now, what I would do first is I would take one of these r's here, and I'm going to cancel one of those r's out with the r that's on the bottom here. So take one of those, cancel it out with the r that's on the bottom here. And so essentially I'm just going to take that 8.37 times 10 to the 6th, so 8.37 times 10 to the 6th. I'm going to multiply it by the 8.450, and then I'm going to divide by the 25.1 times 10 to the 6th power right there. Now, on my calculator, I'm using the E. E stands for times 10 to the, so this 25.1 E6 is 25.1 times 10 to the 6th. If you don't use the E, if you just write out times 10 to the 6th, then you do need to put this in parentheses. Otherwise, your calculator will divide by 25.1 and get the result, and then it will multiply by 10 to the negative 6th power. You need to make sure that it's dividing by all of this. Otherwise, you're going to get a power of 10 error. You're going to end up getting the wrong times 10 to the whatever power. So when I do that, you'll notice that I end up getting about 2,800. And so my final velocity is approximately 2,000. I guess I do have 3 significant figures on all these numbers, so I'm going to go 2,820 meters per second. Now, does that make sense with what we know and believe? Well, yes. We were talking about earlier that as it goes away, the gravity is going to be doing work on our satellite, so it's going to be losing energy, and it should have a lower kinetic energy. Recognize that the height is greater, the distance is greater, so it has more gravitational potential energy, but it definitely has less kinetic energy at that point, which is shown here. So hopefully that was helpful, and check out a couple more of my videos if you think it might be helpful for you. See you later.